Hello everyone, and welcome to the projectile motion post-activity. So hopefully you'll get your activity sheet out here and kind of look at it as we work along here and maybe even take a few notes. So you figured out the effect of changing the angle on the range or horizontal displacement. And then you graphed the range in meters versus the angle in degrees. And the graph you got looks something like this, a parabola. So what did it take to linearize that graph? Now that wasn't really obvious, and so I kind of helped you along here by choosing something for you. But when we graphed range versus the sine of 2 theta, that gave us a straight line. And since that straight line was both linear and went through 0, 0, we can say that the range is proportional to the sine of 2 theta. The horizontal displacement is proportional to sine of 2 theta. Now that's not obvious, and that's why I kind of helped you out a little bit here. Although we'll see why it comes out in a little bit. We'll prove that that's the proportionality. Since we did linearize the graph by taking the sine of 2 theta, we can make a y equals mx plus b math model. So y is the range, the horizontal displacement. And that equals your slope. Please write your number in. Okay, I'm going to write a theoretical number in. We'll see where that number comes from shortly. So I'm going to put in 2.93 meters. You might say, where did that come from? You'll see. Just hang on. Put yours in, though, whatever you got in the lab. And then, of course, the x variable is the sine of 2 theta. The y-intercept here is 0, 0, right? So when the sine of 2 theta is 0, the range is 0. Now notice here, though, that's not just one answer. The sine of 2 theta gives you 0 twice. It gives you 0 when theta is 0. And it gives you 0 when it's 90. The sine of 0 and the sine of 180 is 0. And so there's actually two answers to this one. It's kind of interesting. Right? 2 times when the range is, 2 times when the height is 0. Or sorry, when the range is 0. Because if you shoot it off at 90 degrees, it just goes straight up and comes straight down, right? So it doesn't go anywhere horizontally. And if you shoot it at 0 degrees, it hits the ground right away. Now, as you found in the lab, you did a whole bunch of different angles. Which one was it that resulted in the maximum range? In other words, what angle was it that got us the top of our parabola there? That was, of course, 45 degrees. Now, if you think about it, 45 degrees might make sense, because 45 degrees is kind of the halfway. It balances out the y component of the initial velocity with the horizontal component of the initial velocity. If you shoot at an angle greater than 45 degrees, it goes high, but doesn't go very far horizontally. If you shoot it lower than 45 degrees, it's got a longer range, but it doesn't go up very high, so it doesn't spend a lot of time in the air. So 45 kind of maximizes vertical and horizontal velocities. Now, notice here that it works with our equation. The sine of 2 times 45 is the sine of 90, which is, of course, 1. And that's the biggest that the sine of 2 theta can be. Right? So 45 gives us the biggest result in this equation. Now, let's look at what we did here. Okay? We have a range that we don't know. We have an initial velocity of roughly 5.36 meters per second. This was the AP Physics 1 class average. Basically, if I took all of your initial velocities, your muzzle velocities, and averaged them out, this is roughly what it works out to be. Yours might be a little bit less or a little bit more, and that's fine. Use your numbers. Since that initial velocity was at an angle of theta, we can, of course, break it up into horizontal and vertical components. The horizontal component would be hypotenuse cosine of the angle, because it's the adjacent side, so VO cosine theta. And the vertical part, or VOY, would be hypotenuse sine of the angle, since it's the opposite side, so VO sine theta. I'm working symbolically here. We know that the vertical displacement in this case is kind of interesting. It's 0. So this isn't like when we shoot it off the table onto the ground. In this case, it starts at table height and it ends at table height. It's one of the special things about how we set up the equipment. So its initial and final heights were the same, 0. And we know that the vertical acceleration of a projectile is little g, since gravity is the only thing acting on it. Technically, negative 9.8 meters per second squared on the surface of the Earth. We're going to use little g to work symbolically. And t is an unknown variable at this point. So So we kind of have two unknowns. We don't know the range and we don't know the time. Right? How long does it take to go from here back to the table? So we can write two equations. We can look at the horizontal part of the motion, which of course is constant horizontal velocity, and therefore we can use the constant velocity range equation. Horizontal displacement or range is simply velocity times time. Plug in what we know. The horizontal velocity is VO cosine theta, and we run into a problem. We have two unknowns. We don't know what the range is, and we don't know what the time is. However, we can also look at the vertical part of the motion. That, of course, is uniformly accelerated motion. And if we choose the appropriate kinematic equation, in this case the third, which says that the vertical displacement is the initial vertical velocity times the time plus 1/2 gt squared, vertical acceleration. The vertical displacement is 0 since it starts and ends on the table. So we get this. Now, you'll see some math here that's going to help us, so just bear with me here. Since there's a t in this term and a t squared in this term, I can factor a t out. Now, what good does that do? Well, it's saying that this times t is 0. And the only way two things can multiply together and be 0 is if one of them is 0. So that means either t is 0 or VOY plus 1/2 GT is 0. Now look at that math again. Okay. Factor the t out. Since we're multiplying two things together, the only way you can multiply two things together and get one of them to be 0 is if one or both of them are 0. So either t is 0, which kind of makes sense. When is the vertical displacement 0? Before it shoots anywhere. Or this quantity is 0, and this is the more interesting one. So now we're going to work this and solve for t. So move the VOY to the other side by subtracting. Multiply by 2, divide by g. We get time is -2 times the initial vertical velocity over the vertical acceleration. Plug in what we know the initial vertical velocity to be, which is VO sine theta, and we get that the time can be written as -2 VO sine theta over g. What good does that do us? Well, we can plug that quantity into our range equation and thereby eliminate the time as one of our unknowns. So what we have done is what we would call in Algebra 2 solving a system of equations, two equations with two unknowns, by means of substitution. So we solved one equation for t, plug it into the other equation to eliminate t as a variable. Now, put these two equations together, and we get this equation for the range. Now, this doesn't look like much, but we can do some algebra to simplify some things. First of all, I'm going to take this VO times the negative and the 2 and the VO to make VO squared here. I'm going to pull the g out, and that leaves me with 2 sine theta cosine theta. So make sure you're okay with all this, right? Since these are all multiplication and division, they're commutative and associative, so I can rewrite them. Of course, remember, you can hit pause and look at the math anytime you want, right? Now, what good does that do us? Well, some of you that have had trig at this point might be saying to yourself, wait a minute, I know something about 2 sine theta cosine theta. That's right, it's one of your trig identities. I'm not going to prove it. They did that in trig class. But we know from trig that 2 times the sine of theta cosine of theta is the sine of 2 theta. Plug that in, and we get this equation, which says that the horizontal displacement, the range, is equal to the negative of the initial speed squared divided by the vertical acceleration times the sine of 2 theta. This is the theoretical math model relating the range and the angle, but only when the vertical displacement is 0. So this is a special equation. If you're going to memorize this, you have to remember that this is a special case. This won't work if you're shooting it off a table onto the floor. Okay, this has to be from table to table, from floor to floor, from the same height to the same height. You with me there? Now, notice this equation is starting to look more like what we found experimentally. Right? This is theoretical proof here. So compare what we got experimentally. Horizontal displacement is this weird number I threw in there, 2.93 meters times the sine of 2 theta, to our theoretical construct. And look what we have. This is our y. This is our x. Our b is our y-intercept is 0, which means the slope of our graph must be negative VO squared over g. You see that? This is y equals mx plus b form. This is the equation we made from experiment. This is our theoretical. They've got to match up. The only way they can both be true is if our slope, 2.93 meters, is negative VO squared over G. So then the question is it? Well, let's first of all check out units. Let's see if the units agree. So we've got velocity squared, which is meters per second squared, over acceleration, which is meters per second squared. So meters per second quantity squared is a meter squared per second squared over meter per second squared. So one of the meters cancels, the per second squareds cancel, and we're left with meters. So notice the units here match the units that we got on our slope. So that's interesting. That's one point that we must have been going in the right direction. Now what about the number? Well, our class average VO, remember, which is what I used to calculate my theoretical slope, was 5.36 meters per second. Plug that in for VO. Plug negative 9.8 in for G. It's still a vector, remember, it's got an arrow on it. The negatives cancel, and what do we get? 2.93 meters. That's where I got the theoretical slope. So now I would like you to go through and take the theoretical slope, figure out what your theoretical slope should be. Plug in your muzzle velocity squared divided by 9.8 and compare it to your experimental slope, right, whatever that was, and divide by theoretical times 100 and see what your percent error is. My guess is your percent error is just a few, if any, percent off. And it might be even closer to just 1 or 2 sig figs, right? But even going out to 3 sig figs, you probably are still only off by a couple of percent. So it should be pretty convincing that our theoretical approach and our experimental approach actually give us the same result. Now, why might you get some error? There's really 3 things. First of all, how precise did you really measure things? How good were you with the measuring tape and measuring all of your dots and averaging? Second thing was, how consistent is the mini launcher? It is pretty consistent. I mean, your dots should have really been in a pretty small, maybe $half size circle, right? So it was pretty consistent. Here's the biggest reason you're probably getting error that you probably didn't think about. The projectile launcher is spring-loaded, and so as you change the angle, as you increase the angle you shoot it, think about the forces that are acting. Right? When you shoot it horizontally, the only thing that's acting horizontally is the spring. Right? Gravity's acting vertically and doesn't affect that. But as you increase the angle, more and more of gravity acts down the barrel. Right? It works against the spring. And so the net force actually gets smaller and smaller. Now, it's not a big difference because that little metal ball doesn't weigh much. It doesn't have a very big force of gravity. But according to the company, it's as big as 8% difference from 0 degrees to 90 degrees. So your muzzle velocity actually changes. And we were assuming here a constant muzzle velocity the whole time. So that's probably your biggest source of error. It's probably why some of your final positions or final ranges were a little bit different than your initial ranges instead of being perfectly symmetric on the graph like my theoreticals were. All right, so this is probably the biggest difference. That's why when we do a practicum with this at an angle, we're going to use the photo gates to figure out the muzzle velocity. We're not going to figure it out horizontal and then just assume it's the same all the time. Right, so there's some sources of error. But do go back and calculate, and my guess is you really don't have that much error. You should be pretty convinced that what we're finding here as an equation, that our experimental and our theoretical really do match up. Isn't physics wonderful?